Okay, welcome to lecture here. All right, we're gonna start with chapter 12, I think. Be sure you put here if you could in the chat box. All right, let's see here. All right, everything looks good on your side. Yeah, I can see the screen, full screen. It's not small. Hopefully, yeah. Okay. All right, so in this chapter here, we're going to talk. It's small. No, that's not good. All right, let me try that again. Hang on a sec. Perfect. Let's try it here. Let's go with that one. Is that any better or no? Yeah.
Nah, it's still
Still
like
small?
half the screen.
Okay, hang on a sec here. All right, let's go with let's try that one. Better? Yeah.
Yep.
Yep. Perfect. Thank you. All right. Okay, so in this chapter, we're going to be talking about, like I said, we're going to talk about bonding, talk about some stuff that we kind of talked a little bit about in some earlier chapters as well. Electron configuration with things with ions. We're going to talk about the two major types of bonding, which is ionic bonding and covalent bonding. Ionic bonding, as we'll see, is between metal and a non-metal, and covalent bonding between two non-metals, and sort of the differences between all those guys. So let's get it going here. All right. So when we talk about a chemical bond, you know, why do bonds form? What's the sort of the purpose of it? And we sort of talked a little bit about it when we were talking about electron configuration. Really, one of the main sort of reasons that bonds form is the ultimate goal is for everybody pretty much to get to that noble gas configuration. And that's that electron configuration where they will end up with really the same electron configuration as the noble gases. And remember, noble gases are really, really stable, and that's what everybody sort of tries to achieve when they make bonds. And as we'll talk about here in this chapter, there's really two major types of bonding. We're talking about ionic bonding, which is pretty much always between a metal and a non-metal. And as we sort of talked about in sort of earlier chapters and stuff, what usually happens in this case, a lot of times because of those periodic trends, is our metal will lose electrons over to the non-metal. So there's actually a transfer of electrons that occur. And when those transfer of electrons occur in an ionic bond, that is when our metal becomes a cation, which is positively charged, and an anion, which is negatively charged. And again, in an ionic compound, as we'll talk again about in this chapter, there's absolutely no sharing of electrons. So it's 100% that electrostatic attraction between these two guys here that is holding that together. So there's actually no sharing of electrons. It's just that electrostatic attraction between the positive charge and the negative charge that holds basically that unit together. And that's very different than what else we'll talk about in this chapter, kind of mainly in terms of bonding, which would be our covalent bond. And in a covalent bond, it's basically two nonmetals together. And when we have two nonmetals together, what we essentially have is the sharing of electrons. And it's the sharing of electrons which holds that sort of bond together. And as we'll talk about in this chapter, the sharing of electrons may be sort of equal sharing, maybe unequal sharing, but there's some aspect of sharing that's happening there when a covalent bond, when two nonmetals get together. So really a lot of that is about what we were talking about sort of in that last chapter about those sort of periodic trends, because when we get a metal and a non-metal together, they have very different trends in terms of electrons and how they want to maybe hang on to electrons. As we talked about, essentially metals pretty much want to give away their electrons. Non-metals pretty much want to accept electrons. So when those two guys get together, that's essentially what you get, is that transfer of electrons from one guy to the next, the metal to the non-metal. And that's different than when we get two non-metals together, because two non-metals essentially are pretty close to each other on the periodic table, which means that they share very similar type of properties. So the best that they'll sort of do when they get together is they'll decide we'll share some electrons there rather than transferring electrons. So again, that's the major difference between sort of those two types of bonding that we're going to talk about in a little bit more detail in this chapter here. So there really are these forces that hold these guys together. And when you think about sort of electrons and electrons being shared or electrons being transferred, again, there's a lot of that sort of attraction to the nucleus that's important. Again, electrons being negatively charged. So those negatively charged electrons are going to be attracted to the nucleus in both atoms. And especially in the covalent bond, when we're sharing electrons, that sort of attraction, so it wants to hold basically those things together. Now, when we talk about sort of bonding and we talk about electrons, as we'll see in this chapter as well, it really is those valence electrons that we talked about, which are involved here in bonding. So really in bonding, it's only those valence electrons. And if you remember, the valence electrons are the outermost electrons, the ones in the highest energy level. And those are the guys that are involved in bonding. And you can figure out the valence electrons from the group number. So just a reminder that basically the valence electrons equal the group number. So everybody in group 1 has 1 valence electron all the way down to, say, group 8, which has 8 valence electrons. So when a bond sort of forms, or you want to break a bond, there's a certain amount of energy associated with that process, and that's what's known as bond energy. And bond energy is sometimes referred to as bond enthalpy, like delta H we talked about. And we could have bond enthalpy. And it's basically the energy required really either to make a bond or break a bond. And when we talk about sort of making or breaking bonds in terms of energy, when we do have a bond basically together and we want to break it, we do need to put energy in there. So when it gains energy, it basically will be able to break apart. So typically when we break a bond, it's a endothermic process. And when we make a bond, which is obviously the other thing that you do, that's an exothermic process. Heat and energy needs to be released in that case. And if you just kind of think about it, when you want to make a bond, they're kind of moving around a lot. When they lose energy, they kind of slow down and they're able to really come together to sort of make that bond. And remember that in a chemical reaction, that's really all that's mainly happening is on our reactant side or our starting materials. We're essentially breaking all the bonds that are there. And then all those elements will sort of come together in different arrangements, and we'll be making a bunch of bonds on the opposite side or the product side. And that's, again, what happens in a chemical reaction. That's why we have sort of that conservation of elements. We don't gain elements or lose elements along the way, but we basically break everybody apart and sort of reassemble everybody on the other side. Now, typically the idea behind making bonds and so forth is to kind of lower the overall sort of energy that's happening, and the bond formation usually results in a more sort of stable situation. And again, when we think about energy, lower in energy, more stable than something that's sort of higher in energy. So let's take a look at these different types of bonds we've been talking about here. So again, an ionic bond is always between a metal and a non-metal. And you always have that transfer of electrons from the metal to the non-metal. Electrons are transferred basically to make that ionic compound. And we could represent sort of, this type of bonding using Lewis dot symbols or electron dot symbols, they're sometimes called. So, for example, a Lewis dot symbol. And some people just generically call them electron dot symbols. And basically a Lewis dot symbol or an electron dot symbol is essentially the element symbol and one dot to represent each of its valence electrons. So it's basically the symbol and a dot to represent each of the valence electrons. And usually when we sort of draw these Lewis dot symbols, no more than 2 per side is sort of the rule. And if you have 4 sides, obviously you can max out at 8 electrons. And again, sort of what we've been talking about here is the idea that really bonding is to get everybody to the same electron configuration as noble gases. Noble gases are group 8, and thus we max out kind of usually at 8 valence electrons. So if I want to draw, for example, the formation of, say, lithium fluoride, right? And if we think about those two guys, we have lithium, which is 3 valence electron, 3 electrons total there on the periodic table. Electron configuration 1s2, 2s1, as we talked about. Lithium being group 1 has 1 valence electron. So if we were to draw that, it would look something like this. And that would be this is its 1 valence electron here, right? It's outermost. We have fluorine, which is 9 electrons total on the periodic table, which is 1s2, 2s2, 2p5, if I do the math there. And fluorine is group 7, and this is its 7 valence electrons right here. So if we were to draw sort of the Lewis dot symbol for fluorine, it would be a fluorine with basically 7 dots. And what's going to happen in this particular case is because this is a metal and a non-metal, what we're going to get is that transfer of electrons. So basically this lithium electron here is going to transfer over to our fluorine. And it's at that point when it does that, that it actually does gain a charge. So the lithium has now lost that electron, becomes positively charged. The fluorine, on the other hand, has now picked up that extra electron. And when he picks up that extra electron for fluorine, he now becomes negatively charged. And this right here is basically an ionic compound, or it is ionic compound, but this is an ionic bond. There's absolutely, again, no sharing of electrons here. What's holding this together is that positive negative attraction between, say, the positively charged lithium here and the negatively charged fluoride ion in this particular case. And that's what we see down here sort of generically. This is always what happens, again, a transfer of electrons. So why is this sort of important that we have this transfer of electrons? Why do they really want to do this? And it's because if we look at what happens to the electron configuration, like we talked about, when lithium now has a +1 charge, it pretty much has now lost this electron here. And when it does, lithium with a +1 charge has an electron configuration of 1s2, and that is the same electron configuration as helium. So by lithium losing that 1 electron, it has now achieved helium's noble gas configuration. And our fluorine, which picked up that electron that it picked up is going to go right in there. And when it does that, fluorine with a -1 charge, or fluoride, will now have a 1s2, 2s2, 2p6 configuration, or that is the same configuration as neon. And right there is really the heart of really all bonding. And here in ionic bonding, the way everybody's able to achieve noble gas configuration is the metals will lose electrons, the nonmetals will pick up electrons, and at that point, we now have this ionic compound between 2 ions that both have achieved that noble gas configuration, which is a really stable configuration. Questions on sort of what's happening in our ionic bond here?
Yeah, I've got a question.
Yeah.
It's so the beginning when you figure out the valence electrons, how do you know which ones are the valence electrons?
Yeah, so you could do one of two things. You could write the electron configuration like I did on the screen, and basically the valence electrons are the highest energy level electrons. So when you look at 1s2, 2s1,
So because they're both part of 2, would that make them the highest?
exactly. So in the case of fluorine, we had the 5 in the P and the 2 in the S, and they're both on the second energy level, and that's where the 7 comes from. And but the easier way to really do it is if you just look on the periodic table, the group number will equal the number of valence electrons. So if you look on lithium, it's in group 1, and that means it has 1 valence electron, which is this one I X'd out up here. And if you look at fluorine, it has 7 valence electrons, which are these guys here, those 7 electrons, because they're both, as you said, both on the second energy level, which in the case of fluorine would be the highest.
Okay, thank you.
Yep, that's probably the easiest way than writing electron configuration is to really just look at the periodic table, and group number equals exactly the number of valence electrons. Other questions on that? Okay. So let's then talk a little bit about the covalent bonding. We're going to kind of bounce back and forth there, but a covalent bond, as I mentioned before, is really between 2 nonmetals, and because of that idea that we have 2 nonmetals, they're essentially going to want to share those electrons, because really neither one of them, because of their periodic trends, are going to want to give up their electrons. So what's going to happen is when they do come together, as I mentioned, pretty much the best that they're going to sort of agree upon is, well, you can't take my electron and you're not going to give me your electron, so why don't we just do some type of sharing of those electrons? And that's sort of what we envision sort of happens here. If we have 2 hydrogen atoms, for example, here, and hydrogen again is sort of group 1, or not really group 1, but it has only 1 valence electron because it has only 1 electron. Again, hydrogen not really part of any group. So in this case, each hydrogen has a 1s1 configuration. And what's going to happen, because they're both hydrogen, they're both going to basically say, we're going to actually share these electrons. So as you can see here in sort of this diagram, if this is a hydrogen and this is a hydrogen, sort of that area where it crosses is really the darkest blue on the screen. That's sort of the area where we're sharing the electrons between them. And we will make a bond here where hydrogen, basically you could represent it with a line, which shows that these electrons are being shared, or you can represent it with 2 dots like so, which also indicates that these are being shared. Again, these 2 electrons in the middle count for the hydrogen on the left, and these 2 electrons on the middle there count for the hydrogen on the right. So this is a covalent bond when we start sharing electrons. And when we look at a bond such as this, try not to scribble all over the screen here. We will actually talk about sort of how you know it should be a single, double, or triple bond a little bit later on in the chapter. So we'll definitely get into how you determine that. And there's some rules to sort of follow will help you decide if you should double bond, single bond, or triple bond. But this is a covalent bond, and really because these electrons are both really from hydrogen here, we do expect basically these electrons to be shared equally between the 2 of these. And when we do get equal sharing of electrons, so in this case, we would expect equal sharing of electrons. And what that means is basically those electrons that are between the 2 atoms will spend about the same amount of time between both of them. And this is what is sometimes referred to as a nonpolar covalent bond. So a nonpolar covalent bond is when we have equal sharing of electrons. And you would definitely expect that when we are dealing with obviously something like H2, where they are both going to be sharing those electrons pretty much equally with each other. In fact, this is sometimes what is referred to as a pure covalent bond. Now, different here when we draw this is we have no charges here because there is no transfer of electron. And that's different than when we're showing ionic bonding like we saw in the previous one with the lithium and fluoride. When we draw the lithium and the fluoride, you do need to include the charges, again, because that indicates that those electrons have been transferred and there's no sharing of electrons here. So that's why we do include the charges here, because these are both ions. Here, there are no ions, and in this case, they're actually going to be sharing these electrons equally. So examples of this is like water. If you draw water, looks something like this, right? Draw CO2 as well. We'll talk about how we get to all those sort of pictures in just a second. This is, again, what is referred to as covalent bond. This is also what is referred to as, sort of the question was asking, this is really a single bond. And in a single bond, we basically have one line, or you could represent it by two dots or a pair of electrons. And that is different when we have a double bond. And a double bond is represented by two lines. And each line represents a pair of electrons, or four total electrons, or two pairs. And then we also have a triple bond, which is 1, 2, 3 lines represented by 6 electrons, or 3 pairs of electrons. So you can represent these sort of bonds either way, either as lines or dots. I personally use lines most of the time, but if you want to use dots, you can. So let's talk about what's happening here, though, when, say, hydrogen now basically is sharing these electrons. When it shares these electrons, each hydrogen essentially now has 2 electrons. And you may say to yourself, is that good? And it is good. If you look on the periodic table, hydrogen's number 1. And right after hydrogen comes our good friend helium, which is number 2. And what that means is hydrogen essentially just needs to pick up 1 electron to get to helium. 1 electron is all it needs to pick up, or share, I guess, and that gets it to helium sort of configuration, and really a noble gas configuration. So hydrogen is very different in a lot of things, and this is one of the places, especially in bonding. Let's just write that here so we understand that. Hydrogen only needs 2 electrons. So that's a really important thing to remember. People, for some reason, always want a double bond, triple bond, put dots around hydrogen. What that means is hydrogen pretty much only needs to share 1 electron to get to helium and become a noble gas sort of configuration, which means hydrogen will always find itself, when you're drawing anything with a Lewis structure, on the outside, basically with 1 bond. That's essentially what hydrogen should look like. If you decide to use dots instead of the line, you could do it like that. But you should never have hydrogen with like a double bond. You should never triple bond hydrogen. You should never have a hydrogen with dots around it, because it is definitely wrong. Because hydrogen should never, ever, ever go over 2 electrons. So it only needs 2 electrons, so it's always going to look like that. Questions on that there? So, like I mentioned before, when we do get electrons that come from really the same elements, a lot of times, they definitely will always be shared equally. And that's essentially what holds a covalent bond together. You have these negatively charged electrons, and they're sort of attracted to the positive nucleus of one guy, but yet they're attracted to the positive nucleus of the other guy. So it sort of locks them into place between the 2 atoms, and they really can't sort of escape. And what we would expect, again, is that sort of equal sharing of electrons for those guys to basically get to a noble gas configuration. For example, if we look at fluorine, which is F2, each of the fluorines, as we just saw there, had an electron configuration of 1s2, 2s2, 2p5 for each of the fluorines. And again, as we talked about, it is group 7, so it's got 7 valence electrons. So if we imagine what's happening here, we would have a fluorine and another fluorine. And essentially what's going to happen is they're going to come together to share those electrons. And when they share those electrons, what we will end up getting is a fluorine that looks something like this, basically. Draw my dots a little bit better there. And what we have here is, you could represent like this with the line, or again, you could represent it like so with all dots if you like. But more importantly, when we think about sort of the fluorine that's happening here, this fluorine on the left has now got 8 electrons by sharing those 2 in the middle. Fluorine on the right also ends up with 8 electrons Again, moving fluorine really ahead to the noble gas configuration like neon. And both of those guys, through the process of sharing electrons, have now been able to reach that noble gas configuration. And again, that's going to make them really, really stable. And that's sort of the whole purpose of it. Now, when we look at something like this and we look at sort of these structures here, there are different types of electrons that we deal with. So, for example, when we look at all of these electrons here that I'm circling, those should be 2 dots, very badly done. All these electrons here are not involved in any type of bond. And we know that because there's no element symbol on the other side of the dots. So there's nothing there. They're just dots. And all these guys that I circled here, these are all what are referred to as a very creative name, since they are not involved in bonding. These guys here are called non-bonding electrons. Very creative there. So these are what are known as non-bonding electrons. They are also, if you're old like me, and I probably will still call them these lone pairs, people still call them. So somebody says lone pairs or somebody says non-bonding electrons. They're basically the same thing. They're the electrons that are not involved in bond, hence the name non-bonding electrons. And again, they are represented in sort of Lewis structures here as dots, basically. And when we draw a Lewis structure, kind of like what we're drawing here, and we'll talk officially kind of how to do all those, and maybe we'll do it right now, just kind of a preview of it, and I'll answer sort of that earlier question as well. But we always want to show those non-bonding electrons. There's also obviously another type of electron that we see typically in these sort of pictures, and that electron are these guys right here, and these electrons are involved in bonding, and they also have a very creative name. They're known as bonding electrons. So much like the name implies, bonding electrons are the electrons that are involved in bonds. Non-bonding electrons are the ones that are not involved in bonds. And when we sort of draw these guys, we do want to make sure that we represent all of them sort of there. So this might be a little bit earlier than we should maybe talk about this, but since we have these 3 things here as examples, these actually will be very good sort of examples to explain that earlier question that was asked about, you know, should you use a double bond, a single bond, maybe, or a triple bond. So let me just kind of erase some of this here. Got somewhere to scribble. So, and we'll talk more about how to draw these guys a little bit later on in the chapter, but let's just kind of do it here so we can kind of see all that. So when we draw sort of Lewis structures, there's a few really steps that you kind of want to follow to kind of help you get to probably the right sort of structure when everything is all said and done. And the first one is you want to count up the total number of valence electrons. And that is just the total number from the periodic table, count up the total number of valence electrons that are there. If something has a charge, you need to adjust your count. So if something has a positive charge, you need to subtract. If something has a negative charge, you need to add. Once you do that, you want to make a single bond from the center atom to each of the outside atoms. And once you do that, you then want to kind of put all your electrons on the outside atoms until they have 8 electrons, as 8 is a very important number, as we'll talk about here, as we a little bit as well as the octet rule. And they do go on in pairs. And so let's just sort of see how that works for these kind of simpler ones here. So hydrogen, for example, there's obviously 2 times 1, which would be 2 total electrons. So basically in this case, what we would want to do is go 1H and 1H. So these are diatomic molecules, which means there's really no guessing. There's no center atom. So they're just going to line up kind of linear to each other. And we want to make just one bond between them. So in this case, I made one bond using a line. That one bond represents 2 electrons. And now that I'm done, I want to make sure everybody's okay here. So this guy on the left has 2 electrons. This guy on the right has 2 electrons. And as we talked about earlier, hydrogen only needs 2 electrons to get to the noble gas configuration. So again, this would be the proper structure here for H2. Now, if we look at O2, there are 2 oxygens. Each is group 6. That is a total of 12 valence electrons when I draw my picture. So if we follow the same sort of approach here, we're going to go oxygen and oxygen. We're going to make 1 bond. That is now 2 electrons. If I kind of subtract 2 electrons here, I got 10 more electrons to go. So what I want to do is basically put those 10 electrons on as pairs until everybody has 8 except for hydrogen, which is not the case here, so there is no hydrogen. So what we're going to do is 2, 4, 6. That fills up this guy. He has 8 on the right. 8 and 10. At this point, if I look at my picture, I have now put 2, 4, 6, 8, 10, 12 electrons. That is the grand total of what I should have in my picture. And that's why this number here that we calculated is important. This number here is the total number of electrons that you could have in that picture. You can't have any more, you can't have any less. You got to hit exactly on that number. When you're done, you want to make sure that everybody has 8. So if we look at the oxygen on the right, 1, 2, 4, 6, and 8 electrons. So he's happy. Oxygen on the left, 2, 4, and 6 electrons. It is not happy. So at this point, what we need to do is fix that. And to answer sort of an earlier question, this is really when you want to try to make a double bond or a triple bond to fix it. If I just put more dots on the oxygen on the left, I will end up with 14 electrons, which is too many. I can make a double bond in the middle, but I will still end up with 14 electrons. So typically when we make a double bond, what we're essentially going to be doing is taking a pair of electrons and basically moving them in. And when I do that, what I will end up with is a double bond between the oxygen and a line that went crazy there. Let's try that again. We'll end up with that double bond in the oxygen. And we'll end up with the 2 dots here. And now if we count up our picture here, we have 2, 4, 6, 8, 10, 12 electrons total, which is perfect. And each of the oxygens have 8 electrons. So if you count the oxygen on the left, it has 2, 4, 6, 8 electrons with the double bond in the middle. Count the oxygen on the right. It also has 2, 4, 6, 8 electrons by sharing those ones in the middle. Both of these oxygens have now reached 8 electrons and have now made basically the noble gas. So in the case of hydrogen, double bond not needed. In the case of oxygen, we do need to get to that double bond. And the purpose really of the double bond is, as you can see there, to get everybody to those 8 valence electrons. Question on that there. Now, we could look at the same thing for our N2. So if we look at nitrogen, the same sort of situation is going to occur with nitrogen. So if we look at N2, there's 2 nitrogens, each at 7 from periodic table. That is not right. Let's do some math better. That is 5. I'll learn how to count. There we go. So nitrogen is actually group 5, so that's a little bit better. So that is 10 valence electrons when we do that. So if we follow sort of the same approach, right? So we've got a nitrogen and a nitrogen. Usually the first thing you want to do is just make a single bond, and that is 2 electrons. That means, again, I have 8 electrons to go. That's going to go on the outside in pairs. So that is 2, 4, 6. This nitrogen is now full, and 8. Now, when we look at this, I have now placed 2, 4, 6, 8, 10 electrons total. Nitrogen on the right, as I just talked about, has 8 electrons, but our nitrogen on the left has only 2 and 4 electrons. It has not met the octet rule, which means it is not very happy in this situation. So we want to try to fix it like we did here with oxygen. So to fix it with oxygen, we're going to take a pair of electrons and we're going to move it in to make a double bond. And if I do that, I will end up with something that looks like this. And if I count up on the right-hand nitrogen, I have 2, 4, 6, 8. If I count up on the left-hand nitrogen, I have 2, 4, 6. So we did fix it. We got it to 6, but that's still not 8. So in this case, the double bond really didn't fix the problem. And this would be a case where we want to make a triple bond in this case. To make our triple bond, we got to do the same thing. We got to take a pair of electrons and move them in. And when we do, we will end up with a nitrogen that has a triple bond. And if you count up the nitrogens on both sides, nitrogen on the right has 2, 4, 6, 8 with the triple bond in the middle. Nitrogen on the left, 2 dots on top, and 4, 6, and 8 electrons with our triple bond in the middle. This is the correct structure for N2 and why we really have a triple bond in that case. We need to go to that triple bond level to get everybody to 8 so that they are all have that noble gas configuration. Question on that. We're going to talk more about how to do this with more complicated guys and draw them. But that's sort of a preview of sort of the steps that you do in sort of bonding for covalent guys. And it hopefully answers that earlier question. This is why in certain cases, you only need single bonds and everybody's good in terms of that 8 electrons. Sometimes you do need to get to a double bond to allow everybody to get to that 8 electrons in that noble gas configuration. And as you can see here in the case of nitrogen, sometimes you might need a triple bond to get yourself to those 8 electrons. Any questions on that there?
Yeah, I've got a question. So does that single bond in between nitrogen, the 2 nitrogens, is that 2 electrons?
Yeah, so every time you draw a line, it represents 2 electrons.
Okay, so that's 10 in total in the first one with just 1 bond. That's 10 right there.
Are you talking about when it was like single bonded originally?
Yeah, is that 10 electrons in total, including the
10,
bond?
it is 10 electrons. So it would be 2 there, 4, 6, 8, and then 10 right there. Yeah.
Okay.
Other questions? Yeah, so every line, again, so that's what we're talking about, bonding electrons and non-bonding electrons. So we count them all when we're counting electrons. And again, we oftentimes will represent bonding electrons with those lines. So every time you see a line, you could count them as 2 electrons. And so in the case like the nitrogen at the very end, we still only have a grand total of 10 electrons. We have 2 there, 4. This line represents 6. Middle line represents 8. Bottom line represents 10. So we have still a total of 10 electrons in that triple bond with the 2 dots there. Questions on that? Okay. So that was a little preview of sort of the steps to draw some of these things. Let's continue on. So when we do have anything where basically those electrons are going to be shared equally, that is what is referred to as a nonpolar bond. And in some cases, people will refer to it as a pure covalent bond. And that's a bond where you got like perfect 100% equal sharing of electrons. And that's what you would expect with all the examples that we see here up on the screen. They're all nonpolar bonds, but when you take 2 atoms that are basically the same element, they have the same electronegativity, they have the same sort of periodic trends and stuff like that. So they're going to basically share those electrons perfectly equal with each other when they do happen to come together. So what happens when we get things that are not 2 of the same elements that come together? They tend not to share electrons equally, and that gives us another type of covalent bond. And that is what is referred to as a polar covalent bond. So when we take out, say, with that hydrogen, as we can see here, one of those hydrogens and we place it with a fluorine, we get a compound that looks like this. And between hydrogen and fluorine, as we talked about a little bit about electronegativity, I believe in our periodic trends, fluorine is way up here, upper right, hydrogen's over here. And again, in terms of properties, the fluorine is going to want the electrons a lot more than the hydrogen. So what we end up getting is not equal sharing of electrons, as you can see by this pink. If the pink is sort of our electron cloud, you can see a bigger amount of electrons kind of hanging out on the fluorine side. And the result of that is, because the electrons are basically hanging out on the fluorine side, it's going to create a partially negative charge on the fluorine, which is what this symbol represents. That's a delta negative, or partially negative charge. And where the electrons are sort of moving away from is going to become more positive, which is a partially positive charge. This can be represented by an arrow, and sometimes we make an arrow where it points to the side that's more negative, and the back end of the arrow makes almost like a plus sign to the side that's more positive. And this is what is sometimes referred to as a bond dipole. I'll spell that right. A bond dipole. And bond dipoles basically occur when we got unequal sharing of electrons. And that is basically what a polar bond is. A polar bond is an unequal sharing of electrons. So there's sort of three types of bonds that we're sort of talking about right now, or we have talked about here. So just to put them all together so we make sure everybody's clear on the differences here between what we've been talking about. First off, we started out with our ionic bond. And an ionic bond, that is between a metal and a non-metal. And there is no sharing of electron, again, a transfer of electrons. And we get our cation and our anion, basically. And it's that electrostatic attraction that holds that together. On sort of the other end of the spectrum, you have your nonpolar covalent bond. Our people, again, just call it a nonpolar bond in most cases. This is between two nonmetals, and we have equal sharing of electrons. An example would be something like we've been talking about, F2, H2, any of those guys. And like what we have here in the middle is a polar covalent bond, are just called a polar bond, also between two nonmetals, also involves sharing of electrons, but unequal sharing of electrons. And an example of that would be what we see here on the screen, which is HF, our guy right here, which is an example of that. So those are the three types of bonding, just so everybody, again, is clear on what we're talking about here. On one end, we have absolutely no sharing of electrons, and that is always what's going to happen when you take a metal and a non-metal together. Metal always going to get rid of those electrons, become positively charged. Non-metal always going to pick up the electrons, become negatively charged. Electrostatic attraction between those two is what holds that together. Nonpolar bond, which is a covalent bond, different than that, is actually sharing of electrons between two nonmetals, and those sharing is going to be equal sharing of those electrons between those two nonmetals. And again, in the middle, where we have not equal sharing of electrons, but not such unequal sharing of electrons that they've been transferred, we have these polar covalent bonds, or just a polar bond, which is also between two nonmetals, where unequal sharing of electrons. Again, not to the point where it becomes so unequal that the electrons have been transferred like we get over here, and not sharing of electrons nice and equal like we have here. So sort of in the middle between the two, we get this unequal sharing of electrons, which is known as a polar bond, or again, just our polar covalent bond, but most people just call it really a polar bond. Question first off on those three types of bondings that's happening here. Okay, so the question might be, how do I know, is it going to be shared equally? Is it going to be shared unequally? And there really is, when we look at two atoms, there really is one sort of property that we typically look at to try to decide whether or not something is going to be shared equally or unequally. and that is what is known as electronegativity. And I think we might have talked about electronegativity last time when we were talking about periodic trends. But basically, electronegativity, as it says up there, is the ability of an atom to bring electrons towards itself. So it's the ability of an atom basically to attract electrons to itself. And when we look at the periodic table, the general trend in electronegativity is as we go up and to the right, it increases, with fluorine being the most electronegative atom you could have. And as you go down, obviously, and to the left, it decreases. So, you know, as you go, we'll go this way, I guess, decrease. Change that. Heading this way. As you go down, it decreases. So we can use electronegativity values to help us decide whether or not we would expect, if we take these two atoms and put them together in a bond, if we would expect to see either the ionic bond form, the polar bond, or the nonpolar bond form. And a guy by the name of Pauling came up with sort of a value that was assigned to all the elements, and his values ran from 0 to 4. 4 being the most electronegative, 0 being not so much. So if you take the difference in electronegativity values, which is sometimes delta En, so that means difference in electronegativity values, you basically just subtract the two values. Yeah? Higher number from lower number gets you a positive number, is the way you usually do it. And if you do that subtraction and you have a difference in electronegativity that runs from 0 to 0.4, it is considered a nonpolar bond, which basically means it's a nonpolar covalent bond. And it basically means that we would expect those electrons to be shared equally. If you take a difference in electronegativity value, and it is like from like 0.5 to below 2, it is considered a polar bond or a polar covalent bond, where the electrons will be shared unequally between those two. And typically speaking, if you take a difference in electronegativity values of above 2, it is considered an ionic bond. No sharing of electrons, a complete transfer of electrons when you do that. So we could use these values to help us determine whether or not we would expect a nonpolar bond or equal sharing of electrons, a polar bond where we would expect unequal sharing, or an ionic bond where we would get no sharing, a transfer of electrons. And again, it doesn't work perfectly 100% of the time, but pretty close to it. These are usually the cutoffs that we sort of look at to help us decide those type of things. So let us take a look at this and see. So this is an electronegativity table, and obviously it would be provided for you if you need it. But what you can see is we have values from 0 to basically 4. And you can see, as I talked about before, fluorine being our most electronegative with a value of 4. And that's going up and to the right. You can see it gets greater in terms of electronegativity. Going left and down, we have a decrease in electronegativity as well. And we could use these values to determine things like what we would expect to happen if we sort of put two things together. So let's take a look at some examples here, and just to see how we use this to sort of answer those questions. Let's take a look at the first one that we drew earlier, which was an ionic bond, right, between lithium and fluorine, right? So LiF. So if you had LiF given to you, I'll be honest with you, you don't really even need this table. You should know lithium is a metal, fluorine's a non-metal, is going to be ionic, but we could prove it here by looking at the values. So lithium has an electronegativity value of 1, fluorine has an electronegativity value of 4, If you take the difference in electronegativity, that is 4 minus 1, which is a value of 3. 3 is above 2, which means we would expect this to be an ionic bond. This value is above 2. If we take a look at another one like sodium chloride, sodium is 0.9 there on the left. Chlorine is 3. So when I do the difference in electronegativity values, that's going to be 3 minus 0.9. That's a lot of math there. I'm going to go with 2.1 as a number there. And that 2.1 is above 2. So again, we would expect this to be a ionic bond. Now let's take a look at, say, F2, right? F2, fluorine is 4. Fluorine is 4. That would give me a difference in electronegativity of 4 minus 4. That is 0. That is a difference between 0 and 0.4. It is 0. We would expect this to be a nonpolar bond because that difference is 0. Now, this difference of 0 is what I talk about as being a pure covalent bond. Sometimes people will call that, because at a difference of 0, we have perfect equal sharing of electrons as we would expect. If we take a look, say, at HF, which is another one we just saw, hydrogen is 2.1, fluorine is 4. If we take the difference in electronegativity, that is 4 minus 2.1. That is a difference of 1.9. 1.9 is less than 2, so we don't think it's going to be ionic, but it definitely is above 0.4, so we definitely know this is a polar bond. We also know that that is a big difference in electronegativity, so pretty much as we've been talking about, all the electrons are hanging out over here at the fluorine side. Question on how to use this table here. So why don't you try some here? Let's see. Let's say we had a bond between carbon and hydrogen. Is that going to be ionic, polar, non-polar? Let's do potassium and oxygen. Let's do nitrogen and oxygen. Let's do sulfur and oxygen. And lastly, let's do nitrogen and chlorine. All right, so take a minute or two here, use the electronegativity values, take the difference in the electronegativity values, and determine whether or not you would expect these bonds to be polar, non-polar, or ionic. Okay, so let's take a look and see. So again, really what we're looking at, and when we use electronegativity, we're looking at what is sometimes referred to as bond polarity. And bond polarity, much like the name implies, is whether or not the bond between these two elements, just these two elements alone, are going to share those electrons equally, unequally, or not share at all. So if we look at carbon here, carbon is 2.5. Hydrogen is 2.1. So when we take that difference in electronegativity, we get 2.5 minus 2.1. That is a difference of 0.4. 0.4 is still considered a nonpolar bond. So this would be a nonpolar bond. That is really why also the cutoff is 0.4, because pretty much all organic molecules are made up of carbons and hydrogens, and they're nonpolar, so that is sort of where the cutoff is. So that is a nonpolar bond. Now, between potassium and oxygen, potassium looks like it's 0.8. Oxygen looks like it is 3.5. So the difference in electronegativity, again, just take the larger number minus the smaller number. That way you don't get any weird numbers there. Was that 2.7, I think, on that difference? 2.7. And that means that it is above 2, so we would expect this to be ionic. Nitrogen and oxygen. We have oxygen, which is, or nitrogen, which is 3, and oxygen, which is 3.5. Difference in electronegativity would be 3.5 minus 3 gives you 0.5. 0.5 is above 0.4, so we would expect this to be a polar bond. Sulfur and oxygen, sulfur being 2.5, I believe. Oxygen again being 3.5. So our difference in electronegativity here is going to be 3.5 minus 2.5, which is 1. And we would expect this to be a polar bond. Any questions first off on those there? Okay. Last one up here, which is nitrogen and chlorine. Nitrogen is 3. Chlorine here is 3 as well. So the difference in electronegativity is going to be 3 minus 3, which would give you 0. And that would actually be a nonpolar bond. Any questions on any of that stuff there? So let's talk about some things that we see here. First off, as I mentioned before, when you have a metal and a non-metal, metals are pretty much over here, non-metals are up here. That difference in electronegativity is always going to usually give you a pretty good difference, and it's going to be an ionic bond. So like I said before, if you have something like these two guys, potassium and oxygen, you don't even need this table. You know it's a metal, non-metal, it's ionic. It's a pretty safe bet. You don't even really need this table. Now, when we look at something like nitrogen and oxygen, this is nitrogen right here. This is oxygen right here. They're in the same period, and oxygen is further to the right, which means you don't even need this table for that guy either, because they're in the same period. Oxygen is further to the right, which means it should be more electronegative. And because it's more electronegative than nitrogen, you should get a polar bond. So in the case where you have two elements that are in the same period, the one that is further to the right should be more electronegative, and almost a safe bet just to call it a polar bond, because it usually will end up that way. If you look at sulfur and oxygen, sulfur is here, oxygen is here. These guys are in the same group. Oxygen is further up in the same group. And you don't even need the values here either, because oxygen is further up on the periodic table in the same group. So we know that oxygen should be more electronegative than sulfur. And you can make a pretty educated guess that it is going to be a polar bond. So a lot of times, even if you don't have this table available to you, based on the locations of the two things, you can make a pretty educated guess as to whether or not you would expect the bond to be polar, nonpolar, or ionic based on what you see. Now, there are some exceptions, obviously, and when we see nitrogen and chlorine, those are two different elements, but they have the same electronegativity, which means that we would expect them to share those electrons equally. And that is because even though they're different elements, their location on the periodic table, they are what are sometimes referred to as like the diagonal rule. Nitrogen is here, chlorine is here, they are diagonal of each other. And what that means is, although nitrogen is further up, chlorine is further to the right. So they basically cancel their differences and they end up with the same electronegativity value. You see that same relationship here with carbon and sulfur. They are diagonal of each other on the periodic table. Again, carbon being further up, sulfur being further to the right. They essentially will cancel each other out in terms of their electronegativity. So you do see that sort of diagonal relationship occur in a number of sort of locations on the periodic table. You know, same thing here, 2 and 2. Again, diagonal of each other. You have that sort of same electronegativity. So this brings up the idea that for sure, if you have two of the same elements, you will expect them to share those electrons equally. If you have two different elements, probably a good chance they're not going to share them equally, but there is potential they could, depending on their location on the periodic table. Any questions on that there, or how to use this? So again, we use electronegativity to determine whether or not a bond between these two atoms will be sharing those electrons equally, unequally, or really not sharing those electrons. All right. So if lithium and fluorine react, which has more attraction for the electrons is the bond between fluorine and iodine, which has a more attraction. So again, we want to look at electronegativity. So I think it'll let me do that. So it was lithium and fluorine. So obviously lithium is way over here. Fluorine is way over here. So based on electronegativity that increases to the right, we should expect fluorine to be more attracted to the electrons. And between fluorine and iodine, as we can see here, they're in the same group. Fluorine is higher in the group, and we would also expect fluorine to be attracted greater than iodine. So in both cases, fluorine is our winner. It is the most electronegative because of its location on the periodic table. It is as far up and to the right as you could go in terms of increase in electronegativity. We don't worry about anybody that is next to them, because in our next group over here on the periodic table, these are our noble gases. And in terms of electronegativity, they kind of have a zero electronegativity because they're perfectly happy the way they are. So as we've been talking about, that's what everybody tries to achieve, is that noble gas configuration. They have really no interest in gaining, losing electrons. So that's why we sort of max out in terms of the highest in electronegativity right at fluorine. It is the most highest and to the right you could get without going into the noble gases. All right. What is the general trend electronegativity across the row and down column? So as we talked about, again, increases up and to the right on the periodic table. That means that if you have something in the same period or row, further to the right should be more electronegative. And if you have some elements in the same group, further up should be more electronegative. And again, as I was talking about before, that means that you really don't need, in a lot of cases, those actual numbers. You could make a really good sort of educated guess in terms of how the electrons are going to be shared. Questions on that there? So here's sort of the differences in the three types of bonds we were talking about. Again, on the far right, we have very big difference in electronegativity going to cause that transfer of electrons from the metal to the nonmetal, creating our ions. And we create our ions because here we get a full transfer of electrons. So this guy becomes fully positively charged. This guy becomes fully negatively charged. And as we talked about before, our cation gets smaller, anion gets larger. Attraction here between those two things, holding that together, no sharing of electrons. On the other end over here, we have that nice equal sharing of electrons all the way across. And you could almost think of a nonpolar covalent bond as being, I don't want to say neutral is the right way, but it has kind of no charge overall. And it gets no charge overall because those electrons are distributed equally over the entire thing. So because we have that sort of equal distribution of those electrons, we have no side that's more positive, no side that's more negative. And that's different than our polar bond here in the middle, as we talked about, where we have unequal sharing of electrons. So again, our electrons hanging out in this example, more on the right-hand side. And that creates our partially negative charge and our partially positive charge. These guys are partially positive and partially negative because they are still sharing those electrons. There hasn't been a transfer of electrons like we have in an ionic bond. So because there's still some aspect of sharing, we only get a partially negative charge and partially positive charge, as opposed to a full positive charge, full negative charge, like an ionic compound when we get that transfer of electrons. Any questions on electronegativity, different types of bonding there?
Yeah, I've got a question. So if we put that into like a formula or an example, how would that look?
Yeah, so real examples of all three of these are some of the ones that we've seen before. So like H2 would be an example of a nonpolar bond. So when we're talking about just this bond between these two hydrogens, that we would expect these electrons to be shared equally, which means this is a nonpolar guy. Yeah, same nonpolar bond. Same thing with like F2. You know, this would again be considered a nonpolar bond, equal sharing of electrons between those two. And in the case of F2 and H2, because that is the only bond in the entire molecule, these molecules would also be considered to be nonpolar molecules because they basically only have one bond, and that one bond is going to be sharing those electrons equally. And that's different than, say, in the middle guy here, like HF that we saw. Maybe even HCl is another example, for example, of that. In each of these cases, the electrons would be heading towards the fluorine, electrons would be heading towards the chlorine. And although they are sharing electrons here, these electrons, the bonding electrons here, I'll make really dark. These bonding electrons between these two guys, they're going to be shared unequally. And in the case of the H and F, the electrons are going to find themselves sort of migrating towards the fluorine side. And when we do that, we get more electrons hanging out on the fluorine side of this bond. And that's what creates that partially negative charge that occurs there on the fluorine. And the hydrogen, because the electrons are sort of moving away from it towards the fluorine, becomes more positively charged, less electrons in that area of it. And that's what's known as a polar bond, that sort of separation of charge that occurs because of unequal sharing of electrons. HCl, same deal. The chlorine side is going to be more electronegative. So the electrons in this case would also be finding themselves hanging out more closer to the chlorine side than the hydrogen side, also going to create a partially positive charge on the hydrogen. So both of these guys would be examples of polar bonds. And both of these guys would also be polar molecules because, again, it only has one bond, and that bond's polar, which means the whole thing's going to be polar, as opposed to down here where these guys would be sharing these electrons equally and be known as a nonpolar bond. And lastly here, when we get something like our sodium, which has one valence electron, with chlorine, which has 7 from group 7, again, because they have very, very difference in electronegativity, he's like point whatever he was, 0.8 maybe, and he's 3-ish. What's going to happen is that chlorine's going to go, thank you very much, I want your electron. So in the case of sodium chloride, that's where we get that transfer of electron a complete transfer electron, different than here, where haven't been transferred, they're just being shared unequally. But here in this case, we get that complete transfer of electrons, making our sodium become a fully positive cation and our chlorine becoming a fully negative anion. And again, it's that positive negative attraction that holds that together. Absolutely no sharing of electrons, even though we have dots there. They're not being shared at all. It has completely transferred from the metal to the non-metal in that particular case. So something like sodium chloride, any metal, non-metal that comes together is an example of that. Magnesium fluoride, also metal, non-metal, would be an example of that as well. So those are sort of the examples, sort of real life examples of each of these different types of bonds. Questions on that?
Thank you.
You're welcome. Other questions? And sometimes when people talk about bonds, and they don't really talk about too much these days in this terms, but sometimes instead of polar, non-polar, are ionic. And by the way, where your book says zero difference, this is what I was talking about earlier. A perfect zero difference in electronegativity values gives what sometimes people will call, like I said before, a pure covalent bond. So it looks like your book might use that sort of terminology. But when anybody says a pure covalent bond or something like that, it is the same thing as what we've been calling a non-polar bond. Most people call it a non-polar bond. Again, sometimes people will call it a pure covalent bond. And the difference between those two, for example, the real classification difference is carbon and hydrogen. So if you remember, the difference in electronegativity was 0.4, and that is a non-polar covalent bond. And if you take something like our fluorine, which the difference in electronegativity was exactly 0, also a non-polar bond. So the difference between really these two non-polar bonds is, in the case of F2, with that 0, that's why this guy on the right here would be also classified usually or sometimes as a pure covalent bond, because the difference is exactly 0. We got perfect equal sharing of electrons. Although carbon and hydrogen is also considered equal sharing, it really is not in reality. In reality, the carbon is a little bit more electronegative than the hydrogen. And there is that 0.4 difference. And people consider that up to 0.4 difference, even though technically speaking, it is not perfect equal sharing of electrons, is close enough for people to consider as being equal sharing of electrons. So that's why sometimes you'll see this sort of difference in classification where people will go the extra step and go, oh, you have a difference of 0. It's a non-polar bond, but it is also considered a pure covalent bond because that is like as perfect equal sharing as you could get. While people, when this bond over here on the left, would not call it a pure covalent bond because the difference in electronegativity is not exactly 0, but is still considered equal sharing, even though it's not exactly 0. So that's why there's that 0.4 cutoff, and anything up to 0.4 is considered equal sharing, but there is some degrees of differences in the equal sharing part of it. There is like perfect equal sharing, which is your pure covalent and difference of 0. And then there's equal sharing where there's not a difference of 0, but still considered equal sharing. Any questions on any of that stuff there that we talked about? Okay, so we'll wrap it up here for lecture with this one. What we're going to do today, I think we're going to move some stuff around in terms of the lab, but I think today we will finally do experiment 8 that we've, I don't know, been hanging on to for a while. So I think we'll be good. We'll do experiment 8 today. The one that's scheduled for today, which is basically bonding and stuff like that, we will do probably next time. That'll give us a little bit more of a chance to get into more drawings and stuff like that. So so today we're going to do the periodic trends one and get that finally out of the way. And so that should be experiment 8. And like I said, the kind of Lewis structure bonding one for today, we're going to push off, I think, until Wednesday. Any questions on that?
I had a quick question.
Yeah.
For the one with the bonding that we were going to do today for the
Yeah.
activity 9,
Yeah.
are we supposed to do a pre-lab for that, or is that just an activity?
I believe there should be no pre-labs, I don't think, for any ones that are activities. So I will have a kind of a break now, I think, for maybe a week and a half or two of really no pre-labs due until we get back to, I want to say maybe experiment 12, I think maybe might be the next one that will have like a pre-lab. So the ones coming up are kind of activity ones. They're kind of worksheetish. So there's no pre-lab online that you need to do for those.
Okay, thank you.
You're welcome. Other questions?
Will we have homework on like the activities, like writing what or like?
No, you don't have to do any of the like pre-lab if you're asking like the written pre-lab procedures or anything like that, because
Okay.
there's really not procedures for most of them, other than I think maybe this one with the bonding is like you're supposed to open up models, which you don't have. So you don't have to worry about any procedures until we get again back to the experiment 12, I think, where we do the online one. So pretty much any written one will go with like the online ones that she has to do. Other questions? Okay, so let us, we'll start about 12:05. Give everybody a chance to stand up and stretch. And I'll see everybody in a bit. If you didn't put here, make sure you do so. And again, we're going to do the experiment 8 today.